Alrighty. Hello, everybody, and welcome to the wolfSSL live webinar on advantages of TLS 1.3 with senior engineer Sean Parkinson. My name is Kajal Subkota, and I will be moderating this webinar. All attendees will be in listen-only mode. If you have any questions, please feel free to use the Q&A box or raise your hand to be unmuted if you would like to ask the question live, as we do host a Q&A session following the presentation. This webinar is also recorded and will be made available on our YouTube channel shortly after the presentation. And I invite everyone to follow us on Twitter at wolfSSL, as well as all of our other socials. And please feel free to email us at facts@wolfSSL.com if you have any additional questions. And now I'd like to give a brief company overview before we move to the technical presentation. wolfSSL was founded in 2004 by Todd Auska and Larry Stefanik when they realized there wasn't an open source, dual license embedded SSL library available. OpenSSL existed at the time, but there was a demand for an alternative that was easily portable, smaller, faster, available under a clear commercial license, was equipped with a clean and modern API, and offered commercial style developer support. wolfSSL was born into this market need with an OpenSSL compatibility layer. Today, wolfSSL secures over 2 billion connections. We have more than 1,000 OEM customers and dozens of resellers. wolfSSL is made up of almost 40 dedicated employees in 2021, most of which are engineers. This progress is, of course, supported by a strong partner network that we're very proud of, which includes DDCI, NXP, and Intel, for example. Since the beginning, our engineering team has developed several embedded security products, including WolfCrypt with DO178 support, FIP certification and a FIPS ready offering, MQTT up to the version 5 specification, SSH v2, TPM 2.0, a secure bootloader known as wolfboot, as well as Java wrappers and JSSE support, and commercial support for curl. All of these offerings are accompanied by thorough maintenance and support plans up to the 24/7 level. We also offer full service consulting. And now I'm going to hand it over to Sean for the presentation.
Thanks, Kajal. Welcome to the TLS 1.3 webinar. My name is Sean Parkinson. In this webinar, we're going to be discussing TLS 1.3 and the advantages over TLS 1.2 and why you should upgrade. So the course of the presentation will be an introduction to what TLS v1.3 is, how it works, the advantages of TLS 1.3 over TLS 1.2, and the status of the TLS 1.3 deployment, and finally using TLS 1.3 in wolfSSL. So TLS 1.3 is the newest version of the SSL TLS protocol, which is the standard for securing communications over TCP/IP. The standards document was in development for over 4 years, and they needed that time to come up with all the changes needed to improve the security across the board. A lot has changed from TLS 1.2. Many new ideas about how to improve the security and performance of the protocol result in the format of nearly every single handshake message changing, and some new messages being added as well. So let's look at some of the new features. One of the more important changes has been how TLS resumes a session. The old mechanism of sending a session ID requires a server to store state and has been part of many vulnerabilities. So instead, in TLS 1.3, resuming the session is performed with a session ticket. Now, session ticket was an extension to TLS 1.2 and had its own RFC, but now it's the only way to resume and is part of TLS 1.3 spec. The session ticket contains an encrypted copy of the state of the previous handshake. So the server sends the ticket to the client holds on to that ticket, the encrypted ticket, so the client can't see anything, nor can anyone intercepting the messages. And when the client wants to resume with the server, it sends the encrypted data across in the initial handshake. Therefore, only servers with encryption keys can resume sessions. So that's important. You know, if you've got multiple servers out there, then they all need to be able to share the same secret, the same encryption key, so that they can all use the same session tickets. Alternatively, pre-shared keys can be used. So the standard pre-shared key mechanism, where there's a built-in key or a rotating key, that can be used as well, and use the same messages there. Another significant change to resumption is that by default, a key exchange will be performed. So doing Diffie-Hellman or EC Diffie-Hellman to create a shared secret ensures forward secrecy. And this has a cost. I mean, you do have to do a public key operation here on each end, twice on each end. But it's important for the overall security of the handshake that we do this. A new and controversial feature of TLS 1.3 is the zero round trip time handshake with early data. This handshake has the client sending application data protected by a key derived from the previous session with the client hello. So in the very first message. This means you can get small amounts of data from the client immediately rather than waiting for the handshake to complete. As long as the server has that derived key, then they can immediately get a hold of the information. There are security issues with the feature though, as the same key and IV are used each time that you use the same, say, session ticket. There is no forward security also, and therefore the risk of replay attacks. One option is to not actually allow a session ticket to be used more than once. But that's a server feature, and then you have problems on the servers with knowing who's used the key and who's used the session ticket and who hasn't. But in a simple situation, that's fine. Another new feature is post-handshake authentication. This refers to client authentication using certificates. So if a client is connecting to a website where some of the pages need authentication and others don't, then the server can delay client authentication until after it has seen the URI requested. That is, the client auth happens post-handshake. So that means that once the application data has been sent, the server can then choose to send a handshake message again during in the middle of the application data and request that the client send back the handshake messages to authenticate themselves. Also, for long-term connections like VPNs, the keys and IVs can be updated post-handshake using some new handshake messages. This is not a feature that is expected to be commonly used, but a connection that has been open for a day or has had, say, hundreds of megabytes sent across should be rekeyed. This is done by requesting a key in the IV update. So now let's take a look at the advantages of using TLS 1.3 over 1.2 in details. So I mean, there are two major reasons. TLS 1.3 is more secure and has fewer round trips in the handshake, which means a faster renegotiations. So let's start with security. Only secure cipher suites have been included in the standard. It's actually a little misleading, and I'll get back to this later in the slides. But in essence, when performing a full handshake, you must perform Diffie-Hellman style key exchanges. This ensures perfect forward security. That is, each handshake is protected by a unique secret based on the key exchange secret known only to the client and server. There were many groups during the development of the specification that are not happy about this, and it makes monitoring of networks harder. Many email chains went around the working group mailing list. It was finally agreed that the standard must not be weakened for interception. The dangers of abuse or accidentally reducing security are too great. So updates to TLS 1.3 are being written in other standards groups to allow man-in-the-middle style monitoring, but they will not be recognized by the IETF. To assist you with this, we have mechanisms for getting out the keys so that in callbacks, so that you can do this if you must. So yeah, there is support for being able to monitor full handshakes with the Diffie-Hellman style key exchange with wolfSSL. Another security improvement has been to encrypt all handshake messages after the server hello. So the key and IV used for encryption are based on the key exchange secret and are therefore secure. So having as much of the handshake encrypted as possible is for the best. You want to be able to protect all the information that's being sent, no matter how trivial, because people can start, attackers can start profiling the clients and things like that, even if they're not going to be able to use that information to form an attack. So next is the resumption. That resumption has been redone, and I've talked about that previously. So the key derivation function algorithms have also been updated. Previously, the key derivation function was designed by those running the SSL TLS standard, which is not a bad thing, but it didn't have a security proof. TLS 1.3 uses a standardized function that is both an RFC and a NIST standard, and it's known as HKDF or HMAC KDF. So yeah, it's a little bit slower because it's using HMAC rather than just using a couple of SHA algorithms. But once again, the security is important. It's got a security proof, and we know that there's no known attacks on this. So finally, RSA PSS is being used for signatures in the handshake. In the past, the handshake used RSA PKCS 1.5, and it's still in use with certificates for the foreseeable future. RSA PSS, once again, has a security proof and is more secure against attack. And this is welcome given the number of Leichenbacker attacks we've seen in TLS vulnerabilities. TLS 1.2 does support RSA PSS 2 now, but not all implementations do that. And but for TLS 1.3, it's default. You have to use RSA PSS. Okay, so looking at performance, there are now fewer round trips in the full handshake. The handshake was reorganized to have the key exchange performed at the start, resulting in one round trip key exchange. And this means encryption keys are generated earlier. So let's take a look at TLS 1.2 handshakes and compare that to TLS 1.3, and we can see how this speed up is achieved. In TLS 1.2, the client sends client hello to kick things off. The server sends a server hello and certificates messages, and now a key pair is created. The parameters are assigned, and the server key exchange message is sent with the server hello done. So that's on the server side that the key pair is created. In response, the client creates a key pair and calculates the secret and sends the client key exchange, a change cipher spec, and the finish message. So the client has to perform the key exchange, the generating of the key and creating the secret after it's got the negotiated information back from the server. So the server calculates the secret and returns the change cipher spec, the finish message, and optionally application data. So the first application data is sent in the third flight. Now let's compare that to TLS 1.3. In TLS 1.3, it's a lot quicker and simpler. First, the client generates a key pair and sends the public key as part of the client hello. So the client doesn't know yet if the server supports the key exchange algorithm or algorithms it's sent keys for. So you can optionally send more than one key share if you like. So you can do it for ED25519 and for P256 and for a 2048 Diffie-Hellman if you like. That's pretty excessive. You'd probably only send one, but hopefully you'd have an idea of what the server can support. For a closed system, or when some record is kept from previous handshakes, you can be guaranteed, though, that you know which key exchange algorithm to use. Assuming the client is correct, the server will generate a key pair and calculate the secret a whole round trip faster than TLS 1.2. So the secret is used to calculate the keys protecting the handshake messages after the server hello. The server load contains the public key for the client to generate the same secret and therefore is not encrypted. In fact, the server now sends all the information needed to complete the handshake and can even send application data, all in the server's first flight. The client then calculates the secret, decrypts the rest of the handshake messages, and finishes the handshake, sending back application data again, a whole round trip ahead of TLS 1.2. So this is a performance gain for TLS 1.3, especially in higher latency networks. There is another aspect to this. The public key operations are slightly quicker in TLS 1.3, which I can go to at the end, depending upon how the questions go. So a further faster handshake is the zero ITT handshake. Early application data is sent with the client hello as a separate application layer message and encrypted with a key derived from the previous session. To be able to get small amounts of data immediately is great for embedded systems like sensors. So let's take a look at the handshake and see how this is done. So for TLS 1.3, we're now looking at how you can just do zero ITT handshakes and why it's so fast. First, it should be noted that zero round trip handshakes use pre-shared keys in the form of session tickets or shared keys, like a fixed secret. This is because a previous session from which the early data's encryption keys are derived needs to be identifiable in some way. So the client and the server will both generate the same data, and the client will hold on to that as it's needed to encrypt the early data message. The session ticket is encrypted, so only the server can see it, so the client can't pull any information out of that. It has to keep the keys to use to do the encryption of early data separately. The client sends a client hello message with an extension indicating that there will be early data messages following. Also, the standard key share and PSK extensions are included. The first application layer early data message can be included with the client hello in the first flight. So you can see there the early data message is included as part of the first flight in the diagram. That's an application data message. It's not a handshake message. Next, the server responds to indicate that it will be processing the early data and continues with the standard PSK handshake. When the client has finished sending early data and is ready to use the new keys with application data, an end of early data handshake message is sent along with the finished message. Now application data can be sent encrypted with the new keys. So the first encrypted application data message can be sent in the first flight before any round trips have been completed. Further application data can be sent before or after the receipt of the server's first flight and is finalized with a handshake message end of early data. If the server does not support early data or doesn't want to support it from that client, then it can return a server hello without the early data extension, or even send a hello retry request to indicate to the client it may want to change the security parameters. TLS 1.2, the sort of equivalent of this is just doing renegotiation. So you're using a session ID to indicate to the other side, this is the secrets that I want to use from previously, and you actually have to send a message, send it to client hello has to go across, the server has to respond, complete the handshake, and then you can do application data. So getting it in the first flight is a whole round trip ahead again. So to summarize the benefits of using TLS 1.3, only secure cipher suites have been specified to ensure the highest level of security. All handshake messages have server hello after server hello are now encrypted to protect the sensitive extensions and to hide certificate information. Session tickets and pre-shared keys are used to resume a session instead of renegotiation and resumption. The cryptographic algorithms and their usage have been improved across the board, and finally key exchange in one round trip with zero round trip for application data. Okay, so what's the status of the TLS 1.3 specification in terms of the versions of deployment? I mean, is it actually ready to be used out there? Are people using it? There's no point in upgrading to it and trying to take advantage of it if the infrastructure out there is not available for you to take advantage of it. So in terms of the specification, the IETF has released the final version as an RFC 8446, and this is the version that everyone has implemented to. It was released back in August 2018, which is quite a while back, and everyone's had a lot of, most companies have had a chance to implement it into the browsers and the servers. So the web server, so since then, there's been a number of companies advertising their support, in particular web browsers like Chrome, Firefox, Safari, and Opera. They support TLS 1.3 by default. So they're fine with TLS 1.2 servers, but if they can, they will connect with TLS v1.3 because they think it's that good. Other browsers like Microsoft have support in the latest version, from things like the latest version of Windows. And given that common browsers support TLS 1.3, then it's clear that there's web servers out there that support as well. So there are articles on the web explaining how to compile and configure Nginx, Apache, and Tomcat to use TLS 1.3. Also, of note is that that in the July report of SSL Labs SSL Pulse, they determined that 47.8% of the surveyed servers support TLS 1.3. That's nearly half of the top websites out there, the most popular websites, are supporting TLS 1.3. And also Cloudflare and Akamai, two of the biggest CDNs, they offer TLS 1.3 by default or as a standard option. To me, it's clear that the internet infrastructure is moving to TLS 1.3, even though the servers are moving more slowly. It's encouraging to see that uptake, and it's been a lot faster than TLS 1.2. Note that TLS 1.1 and 1.0 are deprecated now, so everyone should be upgrading to TLS 1.2 at least, and even TLS 1.3. Okay. So now I'll talk about using TLS 1.3 in wolfSSL and how you can take advantage of this faster and more secure protocol using wolfSSL. So what do you need to change in your application to use TLS 1.3? Well, nothing. If you use the wolfSSL 2 v2.3 client and server methods, they will negotiate the highest supported protocol in the client and server. If you, there's a question, does wolfSSL TLS 1.3 support LWIP and free RTOS? We support free RTOS. I don't know about LWIP, but I would suggest you ask support for that or a salesperson. So if you want to just use TLS 1.3, then you will have to use the wolfSSL TLS v1.3 client server methods when creating wolfSSL context. Note also that by the default configuration for wolfSSL includes TLS 1.3. So out of the box, file it up by default using the configure command, you will get TLS 1.3. And if you use the wolfSSL 2 v2.3, wolfSSL v2.3 client on server methods, you will use TLS 1.3 if it's possible. Sorry. Now, Cipher suites have changed a bit, as I talked about earlier. Previously in TLS 1.2, the Cipher suites included the key exchange and authentication algorithm. This is no longer the case, as the client's key is sent in the client hello, and thus the negotiation of key exchange algorithms happens separately. And while they were at it, they decided to pull out the authentication algorithm as well as PSK, and they negotiate, and then they are negotiated separately in the client hello too. So the new Cipher suites are as listed. There are only 5 at this time. 2 are using ASGCM of different strengths. Cha-Cha Poly 1305 is there as a backup if ASGCM has an attack found on it. Though having said that, Cha-Cha 20 Poly 1305 can be faster on processors that don't have the hardware support for built-in instructions doing AS and GCM. So on the more embedded chips, there is no AES instruction or GCM help. So Cha-Cha 20 can be faster on Poly 1305. Also, ASCCM was included for embedded systems as being popular in standards for them. These are the strings that you pass in when explicitly setting the Cipher suites for TLS 1.3. So one major change that if you want to support resuming sessions with session tickets, then you can implement a callback that encrypts and decrypts the session ticket application. To set the callback, use wolfSSL context set ticket inc callback. And there's a good example of how to do this in the example server and test.h files in the wolfSSL source tree. We have more recently created a default implementation that includes rotating of keys. Most users, they should be able to use that default one. But if you need something simpler, or you want to store the symmetric keys in a special way, with hardware maybe, or something like that, then you can replace it with this call. And my screen has gone blank. So next is early data as default. As early data has a different security profile as compared to the normal application data, special APIs are provided to read and write it. Only the client can write data, and client applications use the API wolfSSL write early data. Servers may use wolfSSL read early data to receive it. And if the client doesn't send any, then that's okay. The API will return no data. You can continue on with the handshake as normal. To limit risk, you can set the maximum amount of early data in the establishing session using wolfSSL set max early data. This is included with the session ticket, and the server will then know how much data it should read. Any data after that will be ignored. Other APIs for other features, using ephemeral Diffie-Hellman with pre-shared keys is the default behavior, but this can be turned off on the client using wolfSSL context, no DHE-PSK. Extension will be sent in the client hello, and the server can then choose not to perform the key exchange. This makes sense in very limited environments where public key governance are just too costly. It does have a reduced security, but it can be done. Post-handshake authentication is made available on the client side with wolfSSL context allow post-handshake auth, and is requested after the handshake on the server with wolfSSL request certificate. There's also a new mechanism that we've added to allow the client to delay the requesting of a certificate until after the handshake. There is a security risk in doing that. You're not fully authenticating the server, but it's a feature that was asked for by a customer, so we've added that. Key share is an extension sent in the client hello and returned in the server hello containing the public key for key exchange. To use a client hello request to negotiate which key exchange algorithm to use rather than generating one or more upfront, call wolfSSL no key share in clients. But by default, key pairs will be generated for you. To have the key pair for the algorithms you want generated and sent, then call wolfSSL use key share in clients. Only the algorithm or algorithms you specify will be sent. If the server doesn't like any of those, but there are algorithms in common, then it will respond with the client with a hello retry request, sorry, and the client will send a new client hello. A cookie can be sent in the hello retry request to protect against replay attacks using the API wolfSSL send HR cookie. Call to wolfSSL use key share in the server can also be used, create, and can improve performance. The key exchange algorithm to be used between server and client is always the same, and pre-generating the key can save time, which would otherwise be spent waiting for a new connection. Finally, the keys and IVs can be updated post-handshake at any time with the call to wolfSSL update keys. So in summary, RFC 8446 was released in August 2018, and the most popular browsers have support on by default. Also, some web servers can be compiled and configured to have support. The full handshake is faster as the key exchange only requires one round trip to complete. As a protocol, TLS 1.3 is more secure due to the removal of less secure cipher suites and algorithms and the introduction of new, better algorithms like HKDF and RSAPSS. To use TLS 1.3 with wolfSSL, then simply add it to configuration and it will downgrade from TLS 1.3 to the lowest version you support, and you should be. TLS 1.2. Okay, so that's it for the slides. Sorry about that. My screen has gone blank on me, so I can't actually see anything. So are there any questions about anything here.
Yeah, please feel free to use the Q&A box or even the chat box. You can also raise your hand if you'd like to ask the question live, and we'll just unmute you. We have one question here. If TLS 1.3 is enabled, how much will be added to the binary size?
So the TLS 1.3, if you have both TLS 1.3 and 1.2, it's about 60% bigger in terms of the protocol code. So the last time I checked, TLS 1.3 itself was about 5% smaller than TLS 1.2, but yeah, I'm not sure what that is at the moment. But yeah, if you're going to have both, then you're 60% more code.
Okay, awesome. Does wolfSSL have SSL keylog session capture like OpenSSL does?
Yes, it does. We have added that feature. So that allows people to be able to get the keys out, to be able to put that into something like Wireshark and get the packets being able to be decrypted.
And I guess they want to know if the SSL keylog feature will be part of Wolf CLI.
I'm not familiar with what features are in Wolf CLI. Sorry.
No, it's all right. Someone here wants to know what, oh, the question, what like security relevant unit tests are covered by the automated test methods for the wolfSSL TLS library?
Can you say the question again, please, Kajal?
Yeah, what relevant unit tests are covered by our automated test methods?
So our unit tests are quite comprehensive. We cover all the features that we can. TLS 1.3 is tested by default. We try all the different handshake, all the different options, all the different cipher suites that are used. So we have quite comprehensive unit testing for TLS 1.3.
Okay, awesome. And I think those are the last of our questions. Thank you, Sean, for a fantastic presentation. As a reminder to everyone, we have one more question. Is there support for embedded systems with the wolfSSL TLS library?
Yes.
To detect TLS traffic? Yeah.
To detect TLS traffic. Sorry, what was the last part of that question again?
Is there support for embedded systems to detect TLS 1.3 traffic?
We do have support for embedded systems to do TLS 1.3. We do have the ability to get the keys out for embedded systems. What you do with them is up to you. I mean, we have the callback mechanism to do that. So that's all I can. Yeah, if you want to ask a further question to sort of get a bit more information out of me, please do that.
Oh, okay. So I guess they had trouble using compiling TLS 1.3 for their. And then they say it most likely builds okay for PC.
yeah, the configuration files, the user settings.h file or whatever it's called. Yeah, user settings.h file needs to include the option to do TLS 1.3. I'd have to check, but it may even be that it's the default that you don't even have to make it defined to turn it on. It's there by default, but you may have to define something to say include TLS 1.3.
Okay, this person, they have TLS 1.2 enabled and certificates that work with TLS 1.2. Is there a possibility that the certificates need to be regenerated to work with 1.3?
No, the same certificates work fine. There's no changes that require you to change signature algorithms or anything like that for certificates. That they will. We've successfully done that with our testing, showing that the same certificates we use with TLS 1.2 we use with TLS 1.3, and they all work fine.
Okay, awesome. Oh, okay, so they're running into an issue. They're trying to build TLS 1.3 sniffer for their system, and they're running into an issue where it wasn't running as per our demo we have with the TLS 1.3 sniffer.
Okay, yeah, that's another topic that you should take up with support. I like to stick to the advantages of TLS 1.3. Thanks.
Yeah. Alrighty, I think those are the last of our questions. Thank you, Sean, for a fantastic presentation. As a reminder to everyone, this webinar is recorded and will be made available through our YouTube channel following this presentation. If you would like to receive a copy of the slide deck, please feel free to email us at facts@wolfSSL.com. And if you have any additional questions or comments, we'd love to help you. Please email us at facts@wolfSSL.com, and we'd love to get in contact. Thank you so much, everybody. Have a fantastic day.